Welcome back to the Algebra 2 series. Today we are starting the first of several videos on the hyperbola, and you see here we've got our definition in place in a plane, the set of points such that the difference in the distances to two fixed points is constant. Now in the last set of videos on the ellipse, we saw the only change in our definition is this word right here, where in the ellipse, the word was the sum of the distances to two fixed points is constant. And in this case, we're talking about subtracting the distances. Well, uh, ThinkQuest.org has provided us a nice graph of a hyperbola so that I can illustrate a little bit about how that is the case. And I'd like to just pick a point on this hyperbola and show that in this case the fixed point is now this one out here. So we're going to call this our focal point. And they're saying then by this definition and if I think I'm drawing this right, let me just get it go all the way over to that other focal point. Okay, if we take distance 1 and we subtract distance 2, so d1 minus d2, that is equal to a constant length. And as it turns out, the constant length that we get is this length between the two vertices. This length right here is the difference between those other two lengths. Now it'd be hard to show that, but I think you could almost visualize if you take this distance 2 and subtract it from distance 1, then the remaining distance is the same as the distance between the two, what we look to see as vertices. Well, let me erase some of this and show you some of the neat components of a hyperbola. Obviously, we see kind of in the structure of the hyperbola, we see that there are some diagonal lines through a rectangle, and that rectangle, which is formed by these two lengths, the first one going to the right, and that is going to be denoted by A as we saw with the ellipse, and the vertical length being B, and that one's not going to the hyperbola itself, but it's helping to structure the box. Well, notice also in this case that there's a diagonal for that which creates a right triangle. And what we haven't seen, and it's difficult to prove in the hyperbola, but we can do that at a later video, is that this length is the length C, which is also the length from the center out to here. So that's also C. Now, one of the ways that you could convince yourself of that just in this example is notice that this is the number 5. That's 5, 0, 5 units away, and A is equal to 4, and B is equal to 3, and 3 squared plus 4 squared is 5 squared. So you could verify that, but it'd be difficult to prove in this particular case. In any case, we do see that that is how it works. This point is our focus. This point is our other focus. And so it is interesting to see that. The last thing I want to point out is that the hyperbola, because it has this rectangular box, creates asymptotes, and the graph actually goes along these asymptotes on its farthest points. So that's helping us structure the hyperbola. Let's move on from here, and I want to show you a couple of things. Let's start with the next part, which is the actual equation portion. The hyperbola has two general equations. I believe they're called standard form. These are called standard forms. And notice that HK is very similar to what we saw in the ellipse. And the A's A squared and the B squared is the same as we saw in the ellipse. And the difference here is that we have a subtraction in the middle instead of an addition. So just going to take a look at this example a little more closely, we see that the center is at HK, and we see that A is the horizontal length, left and right, to the vertices. So each vertex, or to the vertices, and then B is up and down to what I call box points. And if you remember in the last picture, those box points were simply these points right here on the top and bottom of the box. They don't really represent anything. They're not on the hyperbola. They're not even part of the asymptote, but they help to structure the box itself. So that's how we generate the picture, is those three items are so important. The center, the left, right to the vertices, the up, down to the box points. We create our entire uh, hyperbola from there. And then the last thing we do is we write our Pythagorean relationship c squared is equal to a squared plus b squared. This is definitely a change from the ellipse because in the ellipse you recall the a was the longest value or the longest length going out to the end of the major axis. So if that's a horizontal hyperbola with center hk, then this bottom one shows a vertical hyperbola with hk. And what I've done here is I've created a picture so you could see this a little bit better. hk is backwards in this problem. Notice that the h is with the x, the k is with the y still, which is the way it should be because this one is vertical and this one is horizontal. But because we are subtracting, we have to put the orientation value, what we call the orientation value, first. So the y minus k comes first in the equation, and underneath that is the a squared. The thing that's really tricky about the hyperbola is that the a squared is not representing the dominant value. Keep in mind that a squared plus, a squared plus b squared is equal to c squared in the hyperbola. So we don't look at the a squared or the b squared to try to figure out which one is larger. We simply look at the way that the equation is structured, and in this case, the y comes first, so it must be vertical. What that means, though, in our box, if we come down here to the box, is that this length right here is now going to be our a, this length is our b, which means that the b value always goes to a box point, which is kind of like the point going, that little segment going to nowhere. It simply creates the structure of our box. What the a does, though, is it goes right to the vertex. And so that vertex, and there's a vertex down here in quadrant 4 there, and that's going to go right up along that asymptote. And this one's going to go right along the asymptote here, and then right along this asymptote on the bottom part. What is not shown here is the location of the focus on each side. We can't really tell where that is because we haven't got the values for A or for B. But if we did, we would be able to see, and you can almost see from my picture that it should be this long. So that length, which you see right here, is if you transform that up, that would be the C value. So it should be that hypotenuse length. Hopefully that's fairly accurate. Now in the next video, what we're going to do is we're going to take some of these and actually graph them. Some of the more difficult parts of this would be finding the equation of the asymptote. So for example, here's one. The equation of this asymptote would be in point slope form. Y minus y1 is equal to m times x minus x1. And the nice part about this is if I put this over in parentheses, these two parts can use the center as their point. And the nice part about that is that the center is hk. So that would just be our k, that would just be our h, and all we really have to do is find the m. Now if you're thinking ahead a little bit, you're going to say, wait a minute, isn't the slope of this line already in the picture? It's right here. The rise and the run are actually given in the equation. So not only is the center and all the other parts given, but the slope of our asymptote is also given. So in this case, this particular one would look like this. Y minus k is equal to, and it's rise over run, or A over B, x minus h. And that would be the first asymptote. The other asymptote, this one down here, simply has a negative slope to it. And so you would simply negate the a over b. So that's really sweet that we can find the asymptote equations very quickly. And you'll see me do that in the next example on the second video where I create those and we put them in our little information box. Okay, so that's a little introduction to the hyperbola, and as you can see, it is kind of a complex graph to create and has a lot of detail to it.